Okay, so just before we start recapping Equilibria and making sure we've got our heads around that before we move on to the harbour process, which is the last part of the course that we've got to do, I just thought it would be nice to look at something that just gave us a sort of reminder of some of the stuff that we've done in the C8 analysis, chemistry analysis, and that was particularly about metal ions. So we've got a quote here or a quote from The Wasteland by T.S. Eliot, widely considered one of the greatest poems in the English language. And there is a little bit of chemistry in these three lines. So I thought it would be nice to just start the first lesson considering briefly a connection between chemistry and poetry. So I've already said it's C8 chemical analysis, and this is about metal ions and what happens when basically we burn them, or we put energy into them anyway. So we've got here an example of something with seawood being burnt. It's being fed with copper. We get two very distinct colours, or Eliot is telling us about two very distinct colours. There's green and there's orange. So I'm expecting you to probably tell what's causing the green colour quite quickly, and that is the copper. But what about the orange? What do we think is going to be responsible for causing that orange colour? Well, the main ingredient in the fire is the seawood, i.e. wood that's been reclaimed from the sea. And if we think about the sea itself, and if we think about the using resources topic, C10, and we think about what we learned about the different sources of water, we know that seawater is a salt solution, or more specifically, sodium chloride solution. So that wood has absorbed sodium ions and chloride ions. And it's the sodium ions that are giving us the orange colour. Okay, then now let's look then specifically at Equilibria, and let's have a recap of what we did earlier in the year. So we're talking about dynamic equilibrium, and that has two parts clearly to the name. So we've got the equilibrium part, and we've got the dynamic part. Now, equilibrium just means there's no change observed. So a classic way of thinking about equilibrium is to think about a seesaw which is perfectly balanced. So there's no obvious change happening. But the dynamic part of this term tells us that even though that is the appearance, actually there is something going on. It's a dynamic system. There are things happening. More specifically, both the forwards and the backwards reactions, they're taking place at the same time and at the same rate. So we've got A and B reacting to form C in our example here, and C, well, reacting to form A and B. Now, dynamic equilibrium can only exist if the reaction is taking place in a closed system. What that means is that the chemicals or the substances that are taking part in the reaction can't enter or leave the reaction. They are effectively sealed in, right? That's what's meant by a closed system. You'll often hear talk about the position of equilibrium, whether it lies somewhere to the left or somewhere to the right or somewhere in the middle. And what that's saying is that when the system appears to be not changing or unchanging, that's the equilibrium bit. Do we find that if we were to look inside that system, if we were to look inside that closed container, would we find much more of A and B in this instance? So that would mean that the equilibrium lay to the left. Would we find that there was sort of a roughly equal mixture of A, B and C, which would be a position of equilibrium around the middle? Or would we find a lot more of C, which would be the fact that the equilibrium lay to the right? So in the question being asked here, and it's asking us, what does it mean to say that the equilibrium lies to the right in this particular example of A plus P goes to C? We are saying that there is a lot more of C present at dynamic equilibrium when the system doesn't appear to be changing than there is of either A or B. So we've got a lot more of C than A or B. Now, most questions that get asked in exams are typically about how this position, whether it lies to the left or somewhere in the middle or to the right, how that position is affected by different conditions that we can change. So the three conditions that we are going to look at, the three that we are going to focus on, how do they affect the position of equilibrium, are changes in concentration, changes in pressure, and finally changes in temperature. To help guide us in how changing any of these three things, concentration, pressure, temperature, can actually affect the position of equilibrium, we need to appreciate this thing called Le Chatelier's principle. It tells us that if you make a change in either concentration or pressure or temperature, then the system seeks to oppose this change. What it wants to do is to restore the balance. So what does this really mean? Well, let's start with concentration. And let's consider it with our example reaction here, A plus B goes to C. So we can change the concentration of any of those in theory, right? We could add more A, we could increase the concentration of A, we could increase the concentration of B, we can increase the concentration of C. But let's just focus on one of them. So if I increase the concentration of A, what the Le Chatelier's principle is telling me is that the system seeks to oppose this change. So if I increase the concentration, the system will seek to decrease the concentration. And there is only one way the system can do that, and that is to produce more of C, i.e. to use up A, to reduce the concentration of A. What does that mean in terms of the position of equilibrium? Well, if we're producing more of C, we're going to have less of A and B. So in effect, the position of equilibrium in this example would be shifting to the right. An increase in the concentration of A means the system seeks to oppose that change. It seeks to bring that concentration of A down. The only way it can do it is to produce more of C. And so we say that the position of equilibrium shifts to the right. And we would also say that our yield, or how much of something we make, our yield of C would increase. So increase the concentration of a reactant, make more product. Decrease the concentration of a reactant, make less product. The next thing we can change is pressure. Now this can only be relevant if there's a gas somewhere in the equation. You know, it could be all of the reactants are gases, it could be one of the reactants is gases, it could be the product as a gas, whatever. There has to be gas present in the equation, otherwise it doesn't mean anything to change the pressure. Now if you increase pressure, Le Chatelier's principle tells us that the system seeks to oppose that change. So if you're increasing pressure, the system is going to seek to decrease pressure. So what does it mean to say pressure? Now, pressure is about particles hitting the walls of the container. This is a closed system, so hitting the walls of the container, and we know that pressure is force divided by area. So how can the system change that pressure? The only thing it can do is to reduce the number of particles hitting the walls of the container, and that simple principle lies at the heart of how a change in pressure affects the position of equilibrium. So if we take our example reaction that we've been looking at, A plus B goes to C, and we make the assumption that all of the species in this reaction are gases, then we can consider how changing the pressure would affect this position of equilibrium. So if we increase the pressure in this closed system, and Le Chatelier's principle tells us that the system will seek to oppose that change, and the only way it can reduce the pressure is to make sure that there are fewer particles or fewer molecules, so it's going to shift to the side with the fewest molecules. So in this example reaction, we've got 2 on the left, 2 moles worth, because we've got 1 mole of A, 1 mole of B. On the right, we've got just the 1 mole of C. So if we increase the pressure in the system, the position of equilibrium will shift to the side with the fewest gaseous moles, which is the right-hand side in this example, so we would produce more of C. Similarly, if we decrease the pressure in the system, Le Chatelier tells us that the system will seek to oppose that change, so it will want to increase the pressure back. So it's going to move to the side with the most moles, because that's the way it's going to increase the pressure, more particles hitting the side of the container. So if we decrease the pressure, it's going to move in this example to the left, because we have 2 moles on the left of gas compared with 1 mole on the right. Finally, let's consider changing temperature. I think this is probably conceptually the most difficult to understand, but we'll give it a good go. So we can either increase the temperature or we can decrease the temperature in a system. So let's assume we've increased the temperature. And again, Le Chatelier's principle tells us that the system seeks to oppose that change. So it's going to seek to lower that temperature back. Now, if we think about increasing temperature, what are we really doing? We're putting more energy into the system. And if we think about our energy stores in physics, we could probably best to think about that as a thermal store. So we have increased the thermal store in the system. So if it's going to oppose that change, it wants to decrease that thermal store. Now, energy can't be created or destroyed. That's the first law of thermodynamics. It can only be transferred from one store to another. So thinking about what store we could transfer that increased energy to, the only real viable option is a chemical store. So we need to transfer energy from the thermal store to the chemical store. The only way we can do that is if there is an endothermic reaction taking place. So if we increase the temperature, we're going to favor the endothermic reaction. So we are going to shift to the side that is the result of an endothermic reaction. Similarly, if we decrease the temperature of a system, then we are in effect decreasing the thermal store. And again, the system seeks to oppose that change. So it wants to increase back the thermal store. And the only way we can get a transfer to the thermal store within the system is if we get more of the exothermic reaction taking place. So more energy is released. So the energy in the thermal store increases back. So let's now try and put that into practice. So we've got some, examples here on this table, question 5 or point 5. And let's just, before we actually try and come up with the, decide on the final answers, let's just think about a couple of things here. So we're going to be making the same change to each reaction when we look at, if you look at the right-hand side of the table. So we have, for example, we are increasing the temperature, right? So every time we're going to increase the temperature. Now, one of the things that we said is if we increase the temperature, we increase the thermal store. The system seeks to oppose that change, so it seeks to transfer energy out of that thermal store. The only way we can do that is to transfer it to the chemical store. The only way that the chemical store can increase is if it's an endothermic reaction. So increasing the temperature favors the endothermic direction. The second thing that the question is looking us to consider is how, if we increase the pressure, what effect that will have on the position of equilibrium. And we know that if we increase the pressure, the system seeks to oppose that change. The only way it can do that is to try and reduce the number of molecules that are hitting the walls of the container, because that's what's causing the pressure. So it's going to, if we increase the pressure, we're going to shift to the side with the fewest moles. So let's consider the first question. A plus 2b goes to x plus z. And we're told that the forward reaction is exothermic. And that means that we know that the backward reaction is endothermic. Now we've increased the temperature. We know that increasing the temperature favors the endothermic direction. So we're favoring the reaction that goes from right to left in this first example, which means that we are going to shift the position of equilibrium left. If we now look at pressure, the thing that we've got to consider is how many moles do we have on each side of that reaction equation. So we can see we've got 3 moles on the left, 2 moles on the right. Increasing the pressure shifts to the side with the fewest moles. So in this example, it's going to shift to the right. In the next question, we've got P plus Q goes to 2x. And we know that the forward reaction is endothermic, which means that the backward reaction is exothermic. We're increasing the temperature. An increase in temperature favors the endothermic direction. In this, it's left to right. So the position of equilibrium is going to shift to the right. Moving to pressure, we again consider how many moles do we have in total on both sides of the equation. And interestingly, there are actually 2 on both sides. So there isn't a side with fewest moles. So this is something that's very important to consider or remember. If you change the pressure, it only has an effect if there is a difference in the number of moles on the sides of the equation. Here we have the same number on both sides. We have 2, so changing the pressure can make no difference to the position of equilibrium. So there is no move. Okay, so I suggest you actually pause the video for the moment and try to answer or fill in the table for the next 2 reactions. The A2 goes to X plus Z and the 2P goes to 2C plus D. So if you try and fill in the table, just pause the video now, try and fill in the table, and then I'll give you the answers in a couple of seconds. Hopefully those are the answers you got, but if you had any problems or you're not sure as to why those are the answers, just let me know. So exam questions very rarely use hypothetical reactions, so we're going to look at a real reaction. So this is sulfur dioxide reacting with oxygen to make sulfur trioxide. This is the sort of equation that you could have in an exam question. So they'll always give you the equation. They'll show you obviously there's an equilibrium reaction because they'll have the reversible reaction symbol there, and they're telling us that the forward reaction is exothermic. So let's make a note of that on the actual reaction because it helps us, I think, it helps me see what I'm doing better. So if its forward reaction is exothermic, that must mean that the backward reaction is endothermic. So even before I've started to look properly at what the question is going to ask me, I'm just I'm sort of preempting the question so that I'm ready to answer it in a second. So the question then asks, if the temperature of this equilibrium was increased, what would happen to the equilibrium yield of sulfur trioxide? So when they say equilibrium yield of sulfur trioxide, they're asking you to say, would you get more of sulfur trioxide? If you think you would, then you're going to say that the yield of sulfur trioxide increases. It's a higher yield. If, however, you think it's going to decrease, then you're going to say there's a lower yield of sulfur trioxide. Okay, so the temperature's increased, and we know the system seeks to oppose that change, that increase in temperature, so it seeks to decrease the temperature. So what's going to happen is it's going to favour the endothermic direction, and the endothermic direction in this reaction is from right to left. So we're going to shift the position to the left in this example, which means we are going to make less or have less sulfur trioxide at equilibrium. There's going to be a lower yield. And this would be something like a 3-mark question, and the way that we would structure our answer is as follows. So increasing the temperature favours the endothermic reaction. In this example, that's the backwards reaction, or the one that goes from right to left. That means the position of equilibrium will shift to the left, which means that we will have a decrease in the yield of the sulfur trioxide, or the SO3. The next question is about how pressure affects the yield of sulfur trioxide. So again, before we make our decision about how that pressure affects it, let's just confirm to ourselves how many moles we've got on each side of the equation. So we've got 3 moles on the left and 2 moles on the right. And if we increase the pressure, the system seeks to oppose that change. It seeks to bring the pressure back down. So it's going to favour the side, it's going to go to the side with the fewest moles, which in this particular reaction is the right-hand side. There are 2 moles on the right as opposed to 3 on the left. So we're actually going to increase our yield of sulfur trioxide on this occasion. Again, it's likely to be a 3-mark question, so the way that we would phrase our final answer is as follows. So increasing the pressure favours the side with the fewest moles, that's the right. The position of equilibrium shifts to the right, and there'll be, as a result, an increase in the yield of sulfur trioxide. So I hope that's been a useful recap of equilibria. In the next video, we'll be applying what we've learned here to a specific equilibria reaction, one which is known as the Haber process. So thanks for listening and not falling asleep, and you'll sadly hear from me soon. Okay, thanks.